Hello friends, welcome back to our channel. So today we'll see one more session in compiler design, that is memory allocation strategies during runtime. So here we'll be discussing two strategies for allocating the memory. One is a stack allocation and another one is a static allocation. So we'll see the comparison between stack and static allocation strategies. So let's start the session. So first let us see static allocation. Static allocation. So here the name itself indicates the static allocation means the memory will be allocated during compile time. Memory allocated during compile time only. So before execution, the memory will be allocated to the variables in the static allocation. And here the memory is fixed memory. So memory is fixed throughout the program, so we can't change the memory. Okay, so because it was already allocated during the compile time, so it cannot be changed, and it is very fast access. So all the variables which are allocated using the static allocation will be accessed very fast and also easy for implementation. Easy for implementation. So it doesn't require any runtime allocations. So example, let us take this example. So for example, int x equal to 10, okay, and main function, and let us do this one, right? So the memory will be allocated for integer data type. So this is an integer data type with a name x, we have given x, and it will give some 10. So here it will be some 4 bytes of data. It occupied some 4 bytes of data. So before execution, this particular memory will be allocated, and which cannot be changed. It cannot be changed. So here memory cannot be changed. Okay, once allocated, the memory can't be changed. So one limitation of using this static allocation is, so this doesn't support recursion. Very important, it doesn't support the recursion, the static allocation. So why? Because let us take this one. See, I'll write int main function, and inside the main function, or let us write recursion means a function calling itself. So I'll write here some function name, function, and again I'll write some function. So let it be some x equal to 10, and let us take this one. Okay, this is an example for recursion. I think hope everyone understand, because in the function we are calling the same function, right? So once the function is called, immediately the control enters into the function, and it will create a variable x with a value 10. And once again, there is a function call. Again the same function will be executed. So again one more memory will be created with a name x. So once again it was executed. One more memory will be executed with a value of x. That means multiple blocks of memory will be executed. Multiple memory blocks will be executed. So also there will be memory wastage in using this static allocation. So one more limitation may be wastage of memory. So these two are the limitations of static allocation. So it doesn't support the recursion. Okay, every time a new memory should be allocated. So every time a function calls, a new memory will be allocated. So this is the main reason why it doesn't support the recursion. Okay, and also, so multiple blocks of memory will be created with the same value, so there will be a wastage of memory. So for this reason, we are moving on with the another allocation strategy called stack allocation strategy. So hope you understood. Static allocation, memory allocated during the runtime. Yes. So now we'll see the stack allocation policy. Static, stack. Remember those terms. So the next one is a stack allocation strategy. Stack allocation. So here the stack allocation, the memory can be allocated and deallocated. Both can be done. Okay, allocated and deallocated during runtime. During runtime. So this is most important. So previously the static allocation, the memory will be allocated during compile time. Okay. So here the memory can be allocated and deallocated by you in the runtime itself. Runtime. Okay. So variable memory. It can be using the variable memory. So it is not fixed memory, variable memory. Okay. So it is best for recursion. It is a best for recursion. Why it is best means, so the recursion will be using the stack data structure in order to store the function calls. Okay, so it will be using stack data structure. Stack data structure. So stack, all of you know about the stack data structure, right? So here the last in, first out. Last in, first out. Okay, so here what happens, see, let us write a small function. So I'll write a main function here, some statements and function, some statements, close, and again we will write the function definition, and again some statements, function, some statements, and close. So this is a recursion. This is a recursion. So whenever there is a main function, okay, so whenever there is a function call, whenever there is a function call, see, most important this one, whenever there is a function call, then the stack frame will be created and it will be pushed into the stack. So stack frame, say new term, okay, stack frame will be pushed into stack, right? So that means whenever there is a function, immediately what happens, it will search for the function definition and the control moves towards the function definition, and once the function definition has been completed its execution, again it will come back to the calling function. So that's the concept of a function. Either it can be a recursion or a normal function. So here we are using a stack data structure. What happens, whenever there is a main function, immediately one stack frame will be pushed into the stack. So this is a stack. This is a stack. Okay, and this is called a stack frame. Stack frame. Okay, so stack frame is also called as activation record. So in our previous session we have discussed about this activation record. So whenever there will be a function call, once the activation record will be created and that activation record will be pushed into the stack. Now immediately the execution of function will be started, and again here we are having a one more function. So again one stack frame for that function will be created. Okay, one more function for that particular stack will be created. So now the control goes here, the control moves here, right? Again there is a function definition, so it will be keep on executing. Again we are having a function call, so again a function definition, function call will be recorded. That means one activation record will be created and that will be pushed into the stack. So once it was completed, again what happens, so it will be popped. So once the function call executes, it will be popped and the control moves to that particular calling function. Okay, so whenever this function is created, this will be popped and immediately it will comes to here, and once immediately whenever this completed, again it goes to here. So again this will be popped, next time this will be popped and it will start execution, and again this will be popped and again it will be started its execution. So once this function is completed, and this function will be popped and the control will move towards that particular address. So which will be stored in the stack, not the address, that is a activation record, or a stack frame. We can call it as a stack frame. So whenever there is a function call, one activation record will be created and that will be pushed into the stack. So what exactly available in the stack frame? What exactly available in the stack frame? So stack frame or activation record, what exactly uh, there? So there will be a local variables. So we can use a local variables in the function, subfunction, and also we may have the parameters that are passed from function call to function definition, and once it was completed, automatically it should return the value to the calling function. So it is a return address. So these three are the some of the fields, main fields of a stack frame. That's an activation record, right? So that's why this is a best for recursion. So we are using some stack and we are using the same memory. See, allocation and deallocation at runtime. So whenever there is a function call, one memory will be allocated. So that is a main function will be pushed into the stack. Once it was completed, we are popping. That means we are applying the pop operation. That means removing. Removing is nothing but a deallocation of a memory. So once everything is completed, the stack becomes totally free. So that means the stack is empty, the memory is empty. So this is the advantage of stack. So one is best for recursion. It's a best for recursion. Okay. So coming to the data structure, there is no data structure used in static allocation. So we'll write a small differences among the stack allocation and the static allocation. So hope you understood about the stack allocation, right? It's a runtime. It's a runtime. So the first one is a static allocation and another one is a stack allocation. So coming to the allocation time, it's a compile time allocation. The allocation time will be compile time, and here the allocation time will be runtime. Okay, and also here what we have seen, the limitation of a static is not suitable for recursion. So not suitable for recursion, and this is best option for recursion. So it's the best for recursion because we saw that allocation of, I mean, the memory will be allocated and deallocated during the runtime for every function call. And here we have seen memory wastage. Memory wastage will be there because multiple blocks of memory will be created here. But here memory can be used efficiently. Efficient use of memory. So what is the data structure used here? So the data structure is fixed memory. So there will be no particular data structure. So memory is fixed here. It cannot be changed. But in this case, the stack data structure will be used. And here, no overhead. Why there is no overhead means before executing the program itself, the memory will be fixed here. So there is no overhead. But here we are using a runtime environment. Okay, runtime. The memory is allocated and deallocated at runtime. So some overhead will be there. In this allocation. Okay. So these are a few differences among static allocation and dynamic stack allocation. static allocation and stack allocation. So this is a allocation time. This is a allocation time. Okay, this is a limitation and memory based upon the memory and the data structure and overhead. Okay, and this is also fast, very fast. Somewhat overhead will be there. Okay, it's also fast, so no overhead. So the fast access will be done in the static allocation, right? So hope you understood what exactly mean the static allocation strategy and the stack allocation strategy, and also we have seen the differences among the static allocation and stack allocation. So I'll stop here, and if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.